And so our next speaker is going to be Runqing, and he's going to be talking about verified differential operators in Rock. Eventually.
Maybe I just use it in this way. Okay. Thank you for introduction. I'm Runqing. I'm a PhD student from the Johannes Gutenberg University Mainz, and today I want to present the framework for modeling and verifying differential operators in the theorem pool Rock. And this is a joint work done with my PhD advisor Sebastian Erdweg. And so at the beginning, I would like to briefly introduce incremental computing, which is the context and the background of our framework. So incremental computing mainly investigates how to efficiently update a program's output based when the input constantly changes. So here is a small diagram showing how a typical incremental program works. Oh, sorry. Sorry. So when there is the input reached an incremental program, and when it's the first input, it will just work normally as a normal program, just translating the input to the output. But after that, if there's a change to the input, the incremental program will not rerun the whole program from scratch. Instead, it will try to efficiently update the output by analyzing the mathematical properties of the structures of programs. And this process just repeats every time the input changes. And in the past decades, there are numerous studies that have shown that incremental computing in some cases can be asymptotically faster in theory and gain 10x to 10,000x speedups in practice. So how do we implement incremental computations? There are typically two ways. The first way is called selective recomputing, and the basic idea of selective recomputing is try to reuse the previous subcomputation results when possible. In other words, it just tries to incrementalize the programs by analyzing the dependency graph. The advantage of this selective recomputing approach is they are purely automatic and can be applied to incrementalize any programs. But it also has a fundamental limitation, which is they don't have a notion of change, only a notion of change. So basically, there are only two types of changes in selective recomputing approaches, which is either no change or replace change. And the consequence is that they cannot incrementalize programs by the algebraic properties of changes. And here is a tiny example. Suppose we want to incrementally compute the sum of a list of integers using folding. Here, if we use the selective recomputing approach, it will first build a dependency graph of the computation, which is sum 2 to 5 relates on sum to 2, and sum to 2 relates on sum 2. I use the yellow color to denote the newly computed results in incremental computation, as this is just the first computation, so everything is newly computed. And after that, so consider we insert at 0 at the index 1. So the input becomes 2025. So now what happens, the dependency graph will be modified. As we only insert at the first computation result, sum 2 will not be affected because it is right before the insertion place. But after that, all of the computation relies on the newly inserted elements, which results in many wasteful computation, because we know that actually the integers form a commutative group, so we actually don't have to care about the order of computation. So we only need to plus the original results with the newly inserted elements. So to complement this approach, another approach for incremental computation is called differential updating. And the basic idea of differential updating is we just translate the input change descriptors into output change descriptors. We are changing the differential operators. So we usually use normal operator to refer to the function that maps the input and output, and the differential operators just maps the input change to the output change. Here is a small example of differential updating programs, which is just a network of differential operators. And so we can revisit the previous example via the differential updating approach. So in order to define a differential operator for sum, we first need to check its type, which maps a list of integers to integers. So we need to define changes on the list and the integer type. Suppose there are two types of change to a list, which is either insertion list or deletion. Insert some element at some certain index in the list, or delete elements in some index at some certain index. And the output, the change to the integer, just plus it with another integer. With this change, we can define a differential operator for sum. And so if we just insert something to the list, I think so we just only need to plus we only need to output a change that plus the original results with k. In the other case, we plus it with negative k because it is correct because we know that the integer adds is commutative and its time complexity reduced to constant time. So apparently the differential updating approach is very effective, but it also has some limitations which prevent it to apply into more fields. And there are two limitations. The first limitation is it's very hard to develop correct and efficient differential operators, as I can show you later. And the second limitation is currently there is no general PL framework supports composing differential operators with language constructs like if-then-else recursion, to the best of my knowledge. So our work just want to tackle the first limitation and to capture the essence of the correct and efficient differential operators. So, in order to do that, we define a framework for modeling and verifying differential operators. When we design this framework, we want to ensure that we want to model differential operators that at least meet these two requirements. The first one is probably correct. It's very important, and because we want to do some drop-in replacement for the non-incremental ones for incrementalizer programs. And the second requirement is it must be very efficient, which is the root of asymptotic speedups and the motivation of using incremental computation. And the second requirement also requires our framework to be expressive enough to model these efficient operators. So now let's just dive into the details of our framework. And the first thing I want to introduce is change structure, which defines how a change can change, which defines how data can be changed. And it contains 4 fields. The T means the type of the value, and delta T means the type of the change. And patch is a function that patch a change to a value and get a new value. And as we know that sometimes the value cannot be changed in an arbitrary way. For example, natural numbers cannot be subtracted from a bigger one. So we use a binary relation VC to denote the value, to specify the valid change to a value. And we use the notation O+ to denote the patch function in the following. And here is a small example of change structure on natural numbers. We can first define the change type, which is either add a natural number or subtract a natural number. And when we subtract a natural number, we should be careful because the subtract number cannot be greater than the original one. So we can define the natural numbers change structure in this way. And here is a very interesting question. So what do we want to get from VC? Which means that, as we can see in the change structure, VC is nothing but a custom binary relation. But what we want to do with VC is prevent we doing arbitrary changes on the values. So how do we just visualize VC using the Rock language? And this stuck me for a while. So after that, I just realized what we want VC to do is to make the changes invertible. I specify it with another type class. So we first define an undo operation, which means that we undo a change to a value. And we just can specify a good VC should capture that a valid change can undo an updated value to the original value. So TO plus delta T minus delta T equals to T. This captures most of how the good VC looks like, and I feel it's really cute to share with you. So we can also build some higher order change structures. For example, if we have also already defined a change structure A and delta A, we can also define a change structure which apply a sequence of valid changes to a value of type A. So after that, let's move to the interface of stateless differential operators, which is the most simple form of the differential operators. We specify its signature as a module type, and the parameter A, B, delta B just means the input type, input change type, output change type, and we require that CA and CB are the input change structure and the output change structure. And the parameter f is the origin operator, and the delta f is the stateless differential operator, just maps the input change, the output change. And we capture the correctness of this delta f through two axioms. The first one is if the input change is valid with the input, the output change should also be valid with the original output. The second one is which we usually call as from scratch consistency, which means that if the input change is valid to the value, then we doing recomputation f of x o plus delta x should be equal to update the original output with output change. So here is a natural question. As we can see that in all of the axioms, we all add a precondition for the input change. So we may have the question that is it possible to develop a very smart delta f which can work correctly without VC? Well, actually the answer is no. Because, for example, this is a very simple example. Suppose we have a inc operator just add a natural number by 1. So its differential form is just an identity function you may consider. And here is the fact that if we do an invalid change sub 2 to 1, then it will be I equal to inc 1 o plus delta inc sub 2. The deeper reason is that we're actually doing ambiguous things on the left-hand side, and but the stateless differential operator is not aware of this fact. So this is the first takeaway I learned from this formalization, which is the valid condition is crucial for developing correct differential operators. And we can also prove that it's very easy to prove that stateless differential operators can work on valid input sequential changes. And here are some examples we formalize using our framework, which are some very known facts, such as the selection and union relational algebra operator are all stateless. That's why databases have a lot of incremental computing works. And so as we become more and more familiar with the differential operators, so why not we do a small exercise together to define a differential operator for the trim right function, which is a string function that will remove all of the rightmost white spaces from a string. For example, trim right white space CoqPL white space will delete the right white space. So suppose we only consider three kind of changes for the string, which is append a character or prepend a character or no change. And now let's do these small exercises together. So the first case is what will be the output change if we append a white space to the original input? Because I think the trim right will remove the rightmost white spaces. So adding a white space on the right will trigger no output change. So now let's consider what if we append a non-white space character C to the original input. Yes, because of the time constraint, I just continue. So someone might think that at C, the non-white space character, and if it will be added into the tail. So maybe the output change is append C, which is actually not, because when we add C to the tail, all of the previously trimmed white spaces becomes not the rightmost white spaces. So we actually need to append both of the previously trimmed white spaces and the newly inserted appended character. So the next case is prepend white space. So as the trim right only handle the white spaces on the right-hand side, should it naturally be the output change is prepend white space? Well, actually not again. Because we forget the case that if the original string only contains white spaces, then prepend white space will not get any output change because the output is still empty string. And in the other case, it's just prepend white space. So the last case is prepend C, which if the C is a non-white space character, the output change should be prepend C. I just want to use this example to show that sometimes the differential operators are stateful. And for example, for the trim right, we need to maintain two states, which is the number of trimmed white space and the flag indicating if the entire string was white space. So these two states are crucial for performance and both for correctness. So this is the second takeaway. From this example, we can find that implementing efficient differential operators sometimes require us to maintain custom states, and these custom states sometimes can not be the previously sub-computation results. So with all of this knowledge in mind, let's see the signature of stateful differential operators. So the first part is the same as the stateless one, just specify the input and output change structure. And okay, as we add state to the differential operators, so we use st to denote the type of the state. And what is really cute about this formalization is we realize that we can also add a change structure on the state to simulate the state update functions, because every time we apply this operator, the state has to be updated, and the state update function actually has the same type as the patch function. So we can just abstract it as a change structure, and with the state type we can define the delta f as a stateful computation. And here it comes to the correctness of delta f. In order to do that, we specify a binary relation between the input and state as a invariant and capture the correctness of delta f under the condition that not only the input change should be valid, but also the state should be correct and maintains the invariant. And the last part is about we not only want the stateful operator works correctly for once, but also works for a sequence of changes. So we just define an initialize function that transforms the original input to the state and impose that it should work correctly from the initial state to every updated state. Okay, we successfully proved that the stateful differential operators can also work on valid input changes, valid input sequential changes correctly. So we also do some case studies we successfully use the stateful differential operators signature to model two very efficient incremental differential operators, existing differential operator. For example, the join operator can be incremental, can be incrementalized very efficiently via the join index, which is actually widely used in current database implementation. And another example is incremental aggregation, which we use the aggregation tree to maintain the state at the state. The incremental aggregation are widely used in the implementation of incremental data log solvers. So here's the conclusion. We formalized an open source framework for developing and verifying efficient differential operators in ROC. And we successfully use our framework to model existing and novel differential operators. And our future work includes we will start to consider how to comprise sequential changes, and ultimately we want to develop a standard library for differential operators for the most common data types. Okay, thank you for your attention. I'm happy for any questions.
We have time for questions. Any questions from the audience? Just keep talking.
Hello? Okay, I think it works. So in your slides about invertibility, I assume not all patch has invertible undo, right? So it seems to me you actually want to generalize this definition to like something like taking the patch and the final result. You might want to have like an undo that returns like a set of the possible
change descriptors
values, right? So I'm wondering, do you run into any issues because of this restriction, or is that not?
Yeah, there is a very simple example to show the VC is not that general, which is just a replace change. For example, if we only define the replace change as replace a new value, then it is not invertible. But we can also define a VC, because VC is always true. We can always replace the values. In order to define an invertible replace change, we not only need to specify the newly replaced value, but the old value. So this is just an example to show why this invertibility not always works, but it just very capture a good shape of VC. So what I actually want to share it here. That's the reason.
Any other questions? So maybe I have one. So this invertible class, does that actually show up anywhere else? Like it seems like this wasn't actually, this class didn't appear in any of your other definitions, in particular your definition of the stateful operator.
Yeah, it does not show anywhere because it just by recent finding about it. But I can also tell you prove that the natural number changes or back changes or sequential changes, they are all invertible under my defined VC. This is VC, which is something I see. Yeah.
So maybe one last question while the next speaker sets up.
Hi. Yeah.
Hello?
Hello.
Okay.
Yeah.
You said you have a change structure on the intermediate state used for stateful diff operators. How is that used? Where does that...
Yeah, this is just the starting of a very big incremental computation project. We want to also develop a PL framework that supports stateful differential operators to have a semantics to correctly use them. But this is just ongoing work.
Okay, so you don't currently use the change structure that you've put on the intermediate state for your stateful diff operators?
Oh, sorry, I misunderstand your question. You mean the change structure on the states?
Yes.
Yeah. Okay, I can just yes. Most of the all of the stateful differential operators can define a change structure on states. We can just abstract in this way. I abstract the state update function as a change structure, which is because just because their type is the same. So we can always do it. Yeah, when define the yeah.
Okay.